Let us start with the second axiom, the equation of motion of classical mechanics. It says mass times acceleration. I do this for a single particle only to make life a bit simpler. Mass times acceleration is equal to the force, and I would like to focus on the conservative case, where I can write the force as the gradient minus the gradient of a potential. So for a conservative and velocity independent force. I can write this in components, so the three spatial components of the position vector, mxi double dot equals minus partial du over dxi for all I. I can work on this a little more. I can say the left-hand side, that's the time derivative of the momentum, which is mxi dot. And then I take the right-hand side, I move that to the left-hand side, so I add the partial du over dxi, and this must be equal to 0. Let me introduce a new function, which I call the Lagrangian. The Lagrangian is a function of xi and xi dot, and in general might depend also explicitly on time if the potential depends explicitly on time. And I define it in the following way. It's m half sum over I xi dot squared minus the potential u, which depends on position and might depend explicitly on time. So this is a new function that I would like to introduce, and I call it the Lagrangian, or the Lagrange function. This Lagrangian has the following property. When I take the partial derivative of the Lagrangian with respect to xi dot, then only the first term in the definition contributes, because only the first term depends on xi dot. The derivative of xi dot squared, that gives 2 times xi dot. The 2 cancels with the 2 1/2 in front. And I'm left with m times xi dot. If, on the other hand, I take the partial derivative of the Lagrange function with respect to xi, then only the second term depends on xi, only the potential depends on xi. So I get minus du over dxi. Now you recognize, let's come back to our equation of motion. And you recognize that what we have here, m times xi dot, this can be written as the partial derivative of the Lagrangian with respect to xi dot. And the second term, the gradient of the potential, can be written as minus the partial derivative of the Lagrangian with respect to xi. So in fact, the equation of motion of classical mechanics can be cast into the form d over dt dl over dxi dot minus dl over dxi is equal to 0. And this must hold as the previous equation for all I. Do you recognize the form of this equation? Let's go back to this previous page. Look at the, or maybe we take the case of multiple functions. Let's look at these equations here. These are Euler-Lagrange equations, and they have exactly the same form as the equation of motion as we just wrote it, only that you have to replace f by L, and you have to replace y of x, or yi of x, you have to replace that by xi of t. And so aside from a change of letters, the equations have the same structure. So we see that these are Euler-Lagrange equations. Now this becomes interesting. We have the equations of motion of classical mechanics, and we can rewrite them in a form that they look like Euler-Lagrange equations. Now we know Euler-Lagrange equations express the extremization of a certain functional. The same is true here. If these are Euler-Lagrange equations, then they express the fact that a certain functional is extremized. What is the functional that is extremized? Well, just remember the integral form that we had before. It's the integral from t initial to t final dt, and the Lagrange function is the function that appears in the integrand. So we have the Lagrange function L as a function of xi, xi dot, and t. This is the functional which is extremized. This has gets a special letter in classical mechanics, and it's called the action. And this functional is extremized. So we learn with this logic that the equations of motion of classical mechanics are equivalent to the requirement that the action functional defined in this way with the Lagrange function is extremized. So we have cast the equations of motion of classical mechanics into an extremization condition, an extremization requirement for a certain functional, which is the functional here. One last remark regarding this page here. When you look at the definition of the Lagrangian, you see this first term here this has precisely the form of the kinetic energy. So this is the kinetic energy, capital T. So more generally, you say that the Lagrangian is defined as the difference, not the sum, but the difference between kinetic energy and potential energy. This is really central to the Lagrangian formulation of classical mechanics. This is the key argument. This is how you make the transition from classical mechanics to Lagrangian mechanics. From now on, we will deal a lot with Lagrangians, and the Euler-Lagrange equations will be the starting point for all the problems that we are going to solve in Lagrangian mechanics. A natural question to ask at this point is, what's the use? I mean, it's just, up to this point, it's just a different way of phrasing, formulating the equations of motion, but you may wonder why you want to do this. What we've shown so far is that the equations of motion of classical mechanics are equivalent to the Euler-Lagrange equations that are associated with the extremization condition that the functionale T1, Ti to Tf dt of the Lagrangian is extremal, so the variation of that functionale is 0. With, just for completeness, the Lagrange function being defined as the difference between kinetic energy and potential energy. Important to note, I made the assumption as a starting point that this is a conservative system where I can write forces as gradients. So let me add this here. This is for conservative systems. So this may be your question mark. Why bother? Why do this? Yeah? The key reason is the following. When I write down the equations of motion of classical mechanics in the usual way, as in Newtonian mechanics, then these equations of motion are always coordinate dependent. Yeah? So if I write, say, m mass times acceleration equals minus du over dxi, if I write it in this form, then this differential equation changes. You have to modify this equation of motion when you change coordinates. And this becomes particularly cumbersome when you decide to go from Cartesian coordinates to curvilinear coordinates. So say you want to formulate the problem in spherical coordinates or in cylindrical coordinates. And then it gets really complicated. On the other hand, when you look at the formulation on the right-hand side, this extremization condition is a coordinate-independent statement. Remember the example of the curve length. Yeah? When I say I can characterize a straight line in two ways. I can say in Cartesian coordinates, in a Cartesian coordinate system, the slope, which is dy over dx, is a constant. This has the disadvantage when I go to, say, polar coordinates in 2D, and now my coordinates are r and an angle phi, and now characterize a straight line in polar coordinates. It gets more complicated. So each time you change coordinate system, you have to think about how you reformulate, how you transform this differential equation and how you formulate it in the new coordinates. But if I say a straight line is the shortest line between 2 points, this is a statement which does not refer to any coordinates. Yeah? So this is the big advantage, that this formulation is independent of coordinates. And this has as a consequence, this has two further advantages. Well, the extremization condition is coordinate independent, but when I then go to the Euler-Lagrange equation, then I have coordinates again. But it's much easier in this Lagrange formalism to write down the Euler-Lagrange equations in arbitrary coordinates. Yeah? So it's very easy to go to arbitrary coordinates. I can easily go to arbitrary coordinates, and we will see later that this has the additional benefit that this makes it very easy to incorporate constraints on the system. I would like to show you one simple example which should also help you solve the last problem on your current problem set. That's why it's important to me. And this example is the inclined plane. Consider the following setup, very simple. In 2 dimensions, the third dimension can be suppressed. You have an inclined plane. The inclination angle is alpha. You have a mass m, which experiences a gravitational acceleration g. And this mass m is gliding without friction on this inclined plane. The inclination angle alpha is fixed. One choice of coordinates, and that would be the starting point in Newtonian mechanics. You would use the coordinates x and y, the Cartesian coordinates, and then write down the equation of motion for the mass in these coordinates x and y. In the Lagrangian formulation, it's coordinate independent, and therefore you can choose different coordinates that are convenient to you very easily. And you see that actually there's only one independent degree of freedom for the mass, since it's constrained to move on this inclined plane. There's just one effective degree of freedom, and this effective degree of freedom is the distance of the mass from the origin. So the position of the mass is uniquely described by the distance s from the origin. So one thing we would like to do is, for the coordinates, instead of x and y, we would like to formulate the problem in terms of s only. To do that, we need to understand, we need to know how Cartesian coordinates are related to this new coordinate s. This is very simple. In this case, given s, you can recover the Cartesian coordinate x, simply by multiplying with the cosine of the inclination angle. You can recover y by multiplying with the sine of the inclination angle. In order to write down the Euler-Lagrange equation, you need the Lagrange function. The Lagrange function is the difference of kinetic energy, potential energy. The kinetic energy is given in Cartesian coordinates by mass over 2 x dot squared plus y dot squared, so velocity squared. We can simply insert the transformation rule for the coordinates on the right-hand side, and then this becomes m half s dot squared. This is because sine squared plus cosine squared is equal to 1. This becomes s dot squared. The potential energy U, expressed in Cartesian coordinates, is mass times gravitational acceleration times coordinate y, the vertical coordinate. Again, we can express that in terms of s using the transformation rule. That's mgs times the sine of the inclination angle. This then gives us the Lagrange function as a function of our new coordinate s and s dot, and it doesn't depend explicitly on time because the inclination angle is fixed. That's kinetic energy, so m half s dot squared minus potential energy, and hence mgs times sine alpha. So we have the Lagrange function now expressed in terms of our convenient coordinate s and s dot. Once we have that, we can immediately write down the Euler-Lagrange equation. Euler-Lagrange equation is d over dt, and then dl with respect to the time derivative of the coordinate. This must equal dl over ds. Yeah. And we can simply insert the Lagrange function that we have on the line before. So the partial with respect to s dot gives us ms double dot. No, first s dot, and then we take the derivative with respect to time. This gives us ms double dot. And on the right-hand side, the partial with respect to s gives us minus mg times the sine of the inclination angle. I'm sure in this particular example you could also have obtained this in the framework of Newtonian mechanics, so maybe not a big deal, but it illustrates the principle how you go about deriving equations of motion in Lagrangian mechanics and using non-Cartesian coordinates.